With section 6.8, we want to learn to add, subtract, multiply, divide types of complex numbers. First here, if we define complex numbers, we're talking about the subsets of real and imaginary numbers. Real and imaginary numbers. So, this is what I was alluding to the other day, but didn't go into full detail. We have complex numbers, which break into imaginary and real. Okay? If there's no imaginary part to the complex number, it's real. If there's no real part, if there's even an imaginary part at all, it's imaginary. Then within real, we have our other subsets that we've looked at already. Okay, so complex number include both of those subsets. First, we want to look at what's called standard form. And this is what I kept alluding to. I kept talking about the fact that A and B are important values. A and B, those quantities, really describe the reaction of the system. So if you're studying engineering, the values that A and B take on are really important. So as a result, scientists, mathematicians have accepted this thing called standard form and used it so that everybody is consistent with the way they write things so that A and B are written the same way every time. So whatever the real part is comes first, and you have that imaginary part afterward. Okay, so A and B themselves are real numbers, right? Like B is a number like 3. A is a number like 7. I is the imaginary portion. Okay? I is the imaginary portion that makes B that imaginary part. So let's take an example of this. So if you're simplifying, this would be really easy. Just the rule to remember if you want to jot down is treat them like variables. Okay, treat these like variables. So if these are variables, this is a really easy process. You're simply adding, combining like terms. So in this first one, you have 2 plus 3 gives you 5. And 4i plus negative 5i gives you negative 1i. So part A is really simple. Part B is as well, which is subtraction. So when you're combining terms with complex numbers, just add or combine like terms. For part B, when you see a negative in the middle, just to remember, maybe a little refresher what to remember to do, make it simple on myself. Yeah, switch the signs, please. So make this a positive in the middle, make this a positive here, make this 2 a negative there. So we've got 6 and negative 2 giving me 4, and negative 7i and a positive 4i giving me negative 3i. But again, in both circumstances, part A and part B, we have A plus BI form. A plus BI form. So in the first case, here, right, A would be 5, and B is what? What's B in the first case? Well, what is it? Not one I, but you're close. Not 1. Negative 1. Okay, remember, standard form is A plus BI. So in reality, this is 5 plus negative I. Like that, really. It's A plus BI. So the coefficient is whatever B is, okay? B is the coefficient here, which is a negative 1. And in the second circumstance, A is 4, and B is negative 3. Again, depending on the type, the value of the number, I should say type also, meaning whether they're positive or negative, it has a different effect on a system of feedback. Okay, I talked about that the other day, right? I talked about cruise control for a little while, I think I want a little spiel about that. But the idea of complex numbers and the values of A and B, values of the roots and the poles they're called, take on an effect or have an effect on the problem itself. More detail with this stuff, to be honest, because a lot of the stuff I'm alluding to comes about from calculus. So you're at the point where you're in algebra right now, algebra 2. So you have geometry, pre-calc, calc. So when you get to that stage, a lot of the stuff will become a lot more useful. Unfortunately, the applications of imaginary numbers are so theoretical for a 9th grade math class that I even wrote a bunch of them. The other night I spent a bunch of time trying to research them, and I wrote down like a list of them, and I could even read them to you. But they're not something that you can actually compute right now. So for example, let me just pull up this list I have here. One of them was electrical circuits. So without understanding electrical circuits, without knowing the laws to electrical circuits, without knowing Maxwell's laws, Kirchhoff's laws, without knowing those and understanding physics, you can't really do much with them. But imaginary numbers are used widely. Hang on one sec. Let me try and find this. Go through. So for this example, we're just going to simply multiply. All right, and if we're multiplying these two values, what do we have to do here? Yeah, distribute. Okay, so FOIL the first one, please. Let's FOIL out the first one here. I'm going to distribute this. I'm going to get 12. Outer is going to give me negative 9i. Inner is going to give me positive 8i. And last will give me negative 6i squared. So I double distribute for part A. I can combine my middle terms. Then recognize that I can replace I squared with what? Negative 1. Okay, so the middle terms come together to give you a negative I. That's a 12 in the front. And this is minus 6. Now I squared is really negative 1. Again, recall from the other class from 6-7 that I is defined as the square root of negative 1. So I squared is just always negative 1. So this negative 6 becomes a positive 6. And Mike, we've got the 12, we've got the 6, giving us 18. Very good. Okay, and then we still have the minus I portion. Alright, so the rest is just arithmetic at that point. Once you FOIL it out, just recognize and recall that I squared is negative 1. How about part B? Part B, who could step me through part B? What do you got, Luca? Okay, and I expect that everybody can do it that quickly, maybe not this exact moment, but eventually as you go through it. So you have the 9 minus the 25 giving you negative 16 minus 30i. Okay? Again, the process is identical to what we've done already. So when we multiply polynomials out, it's no different, except that when you see the I squared here, think of this as a negative 1. And negative 1 times a positive 25 is what gives you this negative 25. All right, and then combine like terms, which the 9 and the negative 25 are clearly like terms in this instance. Any questions on parts A and B so far? Good? Does it make sense? Is it easy? I'm seeing like nods or nothing, so I'm assuming we understand. Okay, let's look at part C. So part C, before I go further, what does part C make you think of? What does part C make you think of? Difference of squares. Very good, Niall. Okay? Remember we looked at already binomial conjugates when we had radicals? Part C, these are called, write this down, complex conjugates. Complex meaning what again?
I'm not sure. There we go. No.
Good. The real part being 5, the imaginary part being the 2i, and we have the plus and the minus, so we call them conjugates. Conjugates simply mean plus or minus. So binomial conjugates had a radical involved, and there was a plus and a minus. Complex conjugates, they don't have a radical involved, they've got an I involved. So they're complex, and it's a plus or minus, so they're conjugates. So let's multiply this out. What do you expect to happen? Right.
Well, the multiply the middles will cancel out.
The middle terms cancel. What does that give me as a result then, Ryan?
That would be 4i squared minus 25 and negative 4i squared.
Okay, giving you? I squared is negative 1, right?
Yeah.
So what does it become?
It would become negative,
Which is?
which is 29.
Yeah. And what's interesting is this. You started with multiplying two imaginary things, and you end up with what kind of an answer? What kind? A real answer. So complex conjugates behave the same way binomial conjugates do. Remember, when our denominator was irrational, we multiplied by the binomial conjugate. So imagine the denominator of a fraction was like 2 plus radical 3. we multiplied top and bottom by 2 minus radical 3. So the same thing occurs here. The middle terms, which in this case would be negative 10i, positive 10i, that are here, cancel. All right? Again, because this is difference of squares, really. All right? And it's not obvious that this ends up being difference of squares. Okay? Especially because here, you can see the squares, right? 25 minus 4i squared. That's what I was referring to. Look, right here, there's difference of squares. But when you replace I squared with negative 1, it no longer looks like an example of difference of squares, right? 29 is not a perfect square. There's no minus sign, so you don't see a difference. But you did stem from difference of squares at some point along the way. Okay, 25 minus the 4i squared. So what do you suppose you might do? What do you suppose... I gave the rule already. Okay. Well, what you suppose you might do when you're dividing. When you're dividing, think of it as binomial conjugates, except another complex conjugate. So let's look at this next example. What would you do specifically for this example? How would you simplify something such as this? So that you're in A plus BI form. Because this is not A plus BI form. It is not appropriate to do this. Don't write this down, please. Do not write this down. This is not true. You can't do that. You can't break up the fraction like this and this, right? Cannot do that. So please, I see so many students do that, and then somehow they do this. They say, well, the i's cancel, just leaving me this, and then it becomes just some fractional answer. Okay, you can't just get rid of the i's like that. You cannot do what I'm showing you here. All right, so again, make sure that when you're doing this, that you take a look, and instead, what should you do? And again, it's analogous to this scenario. If I had this, if I had this, I would do something. I'm going to do the same kind of thing. What would I do?
So you would multiply by 5 minus 3i.
Good. Over.
5 minus 3i.
Very good. Remembering that I need to do what? To the top and bottom when I multiply them? Distribute. So you need parentheses if you don't have them because they're not given. Okay, if it helps you to remember, just place parentheses in the top and the bottom. So the numerator is going to be really messy. The middle terms aren't going to cancel. You need to FOIL out the numerator. The denominator, though, you can see that the middle terms will definitely cancel, so the middle terms don't matter in the bottom. But the numerator here does. So 4 times 5 gives me 20. I'm going to do it in steps. Outer gives me negative 12i. Inner gives me negative 5i. And last gives me positive 3i squared. All over a denominator whose middle terms will definitely cancel. So I'm not going to do the middle terms. Okay, I'm not going to. I'm going to just do 5 times 5, giving me 25. And then outer and inner I'm going to skip. And then last is 3i times negative 3i, which is negative 9i squared. Convenience. Convenience. It's always going to be multiplying complex conjugates. So you're always going to have a minus something I squared. Always going to be a minus in the middle. And I squared happens to be what number again? Negative 1. So the denominator is always going to be some number minus a negative. Again, the denominator will be some number minus a negative. So as a result, the denominator is going to be what? Positive. Always. Okay, something you have to write down. These are good notes to jot down. So the denominator becomes 25 plus 9, because it's minus negative 9 really. The numerator, when I combine like terms, becomes 20 minus 17i minus 3. Again, recalling that I'm going to replace this I squared with negative 1, therefore making this a negative 3 down here. So 20 minus 3 gives me 17. So I'm going to have 17 minus 17i over 34. What's 17 minus 17i over 34 going to yield?
1 minus I over 2.
1 minus
1 minus I.
I, good, over 2. You said something else. 1 minus I over 2. How do you know that, Luca? How do you remember that?
Because you take out 17
Okay, remembering please that really what you're doing, if you are ever in doubt and you're simplifying something, you're really factoring it out. Isn't that really what that is? 34 is 17 times 2. The numerator is 17 times the quantity 1 minus I. So the 17s drop off because they're both greatest common factors, as Luca mentioned, giving us 1 minus I over 2. Is this in standard form? What do I have to write it as? Remember, A plus BI form. So how might I write this if it was in A plus BI form?
3 minus 2i.
It's not 2 minus 2i. That would be multiplying both of the numerators by 2, wouldn't it? But it says divide by 2.
Would it just be 0.5 minus 0.5i?
That's one way to write it, yep. It might be easier to write it as a fraction, though, to see it. Some people might see it better. This is really 1/2 minus 1/2 I. It's the same thing, okay, but I'm writing it this way because it's easier to see. Just divide the 2 into both, all right? Again, divide the 2. Whenever you have, a lot of you looked kind of empty-faced up there, like I didn't really know what to do right away, so you should probably write this down. When you divide a monomial, I've said this so many times, a monomial into a polynomial, you need to divide it into every term. Since this term is a 1 can't be divided by 2, so you write 1/2. The coefficient in front of I is really a -1. So this becomes -1/2. Okay, again, divide the monomial into both terms of the polynomial numerator. Questions on this example? I want to do a few more examples to end, but I want to know if there's a question on this. We're good on this? So what's the rule or what's the idea? Instead of using the binomial conjugate, what do you do for these examples?
Complex conjugate.
Good. Multiply by the complex conjugate over itself. Okay? Here. So determine the reciprocal of 7 minus 2i. What is the reciprocal of the number 5? 1 over 5. So what's the reciprocal of 7 minus 2i?
1 over 7 minus 2i.
1 over the quantity 7 minus 2i. So clearly I can see that this is another example like we just did. So how would you approach this? Mike, what do we do?
Divide 2.
It's not a monomial denominator, Mike. We're not at the end of the example like last one. There's a binomial denominator, right?
How would you rationalize?
Yeah, so multiply by
7 plus 2.
over.
7 plus
Good. And just be careful. The word isn't rationalized there, just to give you a heads up. If there's a radical in the denominator, we say we rationalize because it's irrational. What we're doing here is we're converting something that's imaginary, that's not in standard form, to standard form. That's really all you're doing. If the word is not rationalized for this example. But it's the same idea, as Mike had mentioned. Numerator is still good. What do you get for the denominator? Do it quick, come on. Quick. Yeah, because you have 49 plus 4. How do I know that? This gives me 49. This multiplies to negative 4i squared. Negative 4i squared is really positive 4. Again, you don't need to multiply the inner terms. So 7 by 7 is 49. Negative 2i by positive 2i is negative 4i squared. If it helps, I'll write it out in case we're unclear. That's what we really get, which, as Charles mentioned, reduces to 53 in the bottom, the numerator being 7 plus 2i. So what's my final answer? What should it look like? That's what I have right now. How do I write this in standard form always? Always in standard form, by the way. Every answer. Doesn't have to say in the directions. You always express complex numbers in standard form. What would it look like, Ben?
7 over 53 plus 2 over 53.
Very good. Yeah, or no, the way you had it the first time is better, actually. Because what it does, You can write it as 2i over 53, but then you're combining the real and imaginary part. You have real plus real imaginary. A plus bi form. Okay? So A is 7/53 and B is 2/53 in this scenario. And last but not least, a mess of a problem. Similar to the ones we've done, but I want you guys to be familiar with evaluating functions. It doesn't matter if you're evaluating with a real or imaginary number. So if g of x equals x over the quantity x plus 1 squared, determine g of 1 plus 3i. What does it mean when it says determine g of some number? What do you do with that number, Niall? Plug it in, plug it in. Okay, take this quantity here, plug it in here, and plug it in here. The numerator becoming 1 plus 3i. The denominator becoming the quantity 1 plus 3i plus 1 squared. Now, please don't square the denominator just yet. Combine the ones. Make it easier on yourself. There's a lot of steps to this problem. Now, at this point in time, some students might get stuck and try to multiply by the complex conjugate to start. Why can't I do that? Why can't I multiply by 2 minus 3i over 2 minus 3i?
Because the quantity is squared.
Quantity is squared. We have 2 of those in the denominator. So why don't you FOIL out the denominator first? So think of the denominator as 2 plus 3i, 2 plus 3i. Okay, multiply out the denominator by itself first. So the numerator, leave it alone. Write the denominator like this. Because that's what squared really means. And then FOIL out the denominator. And what do you notice? You FOILed out a denominator that was a squared binomial to leave you with simply a binomial. That's the interesting part. You started with 2 plus 3i squared, right? And when you multiply this out, you get this. But this is just a simple binomial. This is 4. This is a negative 9 over here, giving you negative 5 for the real part. And then a 6i and 6i is 12i. So as a result, by multiplying out the denominator or FOILing it out, this gives me a single binomial denominator. Now what can I do?
Rationalize.
What's the other term though? Remember, if it's not irrational, I wouldn't use rationalize. Just say multiply by the...
Complex conjugate.
Okay, much better. Again, I understand it looks like it's the same process as rationalization, but it's not the correct word there. What's the complex conjugate of negative 5 plus 12i? Well,
Negative 5 minus 12.
good. What do you think the common mistake would be there, Will? Or what do you think might throw off some students?
5 minus 12.
Yeah. The negative 5 might throw some students off and say, oh, I got to switch that. But recall that what you're really switching, all right, is the imaginary part. So that when you multiply these two out, you get a negative answer. For the imaginary part, you have the negative I squared there. What does this give me as a result? The numerator is going to be messy. I'm going to FOIL negative 5. Outer is going to give me 12i. Inner is going to give me negative 15i. And last will give me 36i squared. The denominator, much easier. Negative 5 times negative 5 is still positive. We kept saying this. The denominator is always going to be positive if we do this the same way. And then it's going to be a minus 144i squared. Simplifying further. Again, that's why I said this is a messy problem. Simplifying even further, what do I have? Numerator. Kelly, help me out with the numerator.
You get 31i squared minus 3i.
I agree with you that we have a minus 3i.
Is that 36i or 36?
Oh, no, it is squared. Sorry, it's off the screen, but it is squared. Yeah, there it is. Sorry. But it's not, you can't combine negative 5 and 36i squared.
Yeah, but when I squared becomes negative 1.
So there's no I squared, right?
No.
Okay. You said, yeah, you see what I'm saying now?
Yeah.
Okay. So this is really negative 36. And this is negative 5, giving you negative 41. Okay, be careful. Because you said negative 31i squared. Remember, the I squared is gone now. Okay, the I squared is gone now. That makes sense? The numerator part? Okay, making that negative 36 there, combining with the negative 5. These two things give you negative 41. The denominator is 25 plus 144, which is 169. Would I leave it like this? No. How would I write my final answer, Roy? If I wanted an A plus BI form?
Oh, you would, do negative 41 over 169, and then, you do minus 3 over 169.
Okay, and now, are any of these divisible? Can these be reduced? 3 and 169 cannot. How do I know? Add the digits of 169 together. What do they come out to be? 16, right? Is that divisible by 3? So that means that number's not. You know that rule or no? Little trick? Same thing works with number 9. Add the digits of any number. If it adds up to something that's divisible by 9, then that number is divisible by 9. It's a number trick with 3 and 9. Just for quick knowing reductions. And then here, 41. 41 is a prime number, right? So I don't have to worry about that. You can leave that alone. So I have the A value is negative 41 over 169. The B value is negative 3 over 169. And we have A plus BI form. Alright? Again, this is a skill. I can't impose or emphasize that enough. The stuff you did with radicals. Algebra 2 can be a bit, boring and redundant because you learn skills in Algebra 2. When you apply those skills, not until you're in count. You will apply the stuff you're learning here, you will. But the unfortunate part is that you really don't do a lot of those applications for the skills that you learn. What you're going to what you're going to apply is the stuff next chapter. Chapter 7, Chapter 8, with parabolas, we're going to see a lot of interesting applications. This is really, honestly, boring stuff. You're just learning skills right now. But you have to learn these skills to understand what you're going to do later, to be able to actually make use of this material. Okay, so you need to practice these skills.